Last example for rotational kinematics, I promise. So example number 4, it says we are given the job of designing a large horizontal ring that will rotate around a vertical axis that will have a radius of 33.1 meters, blah, 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 blah. Passengers will enter through a door in the outer wall of the ring and then stand next to the wall. We decide that for the time interval 0 to 2.3 seconds, the angular position theta, oh my gosh, theta of a reference line on the ring will be given by theta is equal to ct cubed, with c equal to 6.39 times 10 to the negative 2 radians per seconds cubed. After t equals 2.3 seconds, the angular speed will be held constant until the end of the ride. Once the ring begins to rotate, the floor of the ring will drop away from the riders, but the riders will not fall. Indeed, they feel as though they are pinned to the wall. For a time t equals 2.2 seconds, let's determine the rider's angular speed omega, linear speed v, and angular acceleration alpha, tangential acceleration a sub t, and radial acceleration a sub r, and acceleration a. Whew, that's a lot. Okay, let's do it. So first and foremost, I hate when they do this in the book, when they give you a function and they say like c times t cubed, and then they just give you c. Like, why don't they just put c in the function? It's very annoying. So what's happening here is that we're speeding up until 2.3 seconds and then going at a constant angular velocity after that. But we're looking at a time t equals 2.2 seconds. So we're still speeding up at this time. So in order to find our, or I guess it's not, there's no parts like A, we're just finding different things. So it says we want to find our angular speed, linear speed, angular acceleration, both linear accelerations, and our overall linear acceleration. So let's first start with omega, our angular speed. So of course, when we're going from position to velocity, we're going to take the derivative. So here we want to take the derivative of our position function, which I'm actually going to write up here. And that was 6.39 times 10 to the negative 2 radians per second cubed times t cubed. So when we are going to take the derivative, I'm going to take that 3 on the t cubed, multiply the thing before t time by 3, and then I'm going to subtract 1. So we end up getting 3 times 6.39 times 10 to the negative 2 power times t squared. So for this, we end up getting, where's my calculator? 3 times our 6.39 times 10 to the negative 2. And that is just 0.1917 t squared. And then, of course, we're evaluating this at time t equals 2.2 seconds. So I'm just going to plug that in for my time. .2. So I'm going to multiply this by 2.2 squared. And we end up getting our angular velocity at this time is equal to 0.93 radians per second. So that's our first answer. Next, we want to find linear speed. So remember, when we're looking at linear values and we're getting them from angular values, we use this equation here. This one is on your equation sheet. So the linear speed will just be this angular speed, 0.93 radians per second, times the radius, which they give us is 33.1 meters. So here we end up getting 0.93 times 33.1, which is 30.8 meters per second. Now, a little note about this, you'll notice that the unit radians kind of just drops here because we get meters per second for our linear speed. And it's kind of like, I don't know, I like to call it like a ghost unit almost, because it is there, but when we do math like this, it's just the unit radians doesn't really matter, just kind of goes away. It just goes away. The ghost unit. So that's our answer for our linear velocity. And then we want to find angular acceleration. So just like when we go from position to velocity, when we go from velocity to acceleration, we take another derivative. So acceleration as a function of time will be the derivative of this 0.1917 times time squared. So I'm just going to multiply 0.1917 times 2, subtract 1 from that exponent. So for angular acceleration, we end up getting 0.3834 t. And then, of course, we're evaluating at 2.2 seconds. So the angular acceleration is equal to 0.3834 times 2.2, which ends up being 0.84348. So about 0.84 radians per second squared. That's our angular acceleration. And then remember, our tangential acceleration is found from, oops, I did that backwards. My bad. Tangential acceleration is equal to angular acceleration times radius. So now we're just going to take this number, 0.84, and multiply that by the radius, which was 33.1 meters. So again, we end up getting tangential acceleration. So I'm just multiplying this by 33.1, and we get 27.9 not radians, my bad. Acceleration is in meters per second squared. Again, that radians unit just kind of drops out. That's tangential linear acceleration. And of course, we have radial linear acceleration as well. Radial acceleration, remember, is just centripetal acceleration, which is v squared over r, which in this case, our linear velocity was 30.8. So we get 30.8 meters per second. We're going to square that, divided by the radius, 33.1 meters. So 30.8 squared, and then divide that by 33.1. We end up getting 28.66 meters per second squared for our radial acceleration. And then we want to find overall acceleration, which of course is going to be made up of tangential and radial acceleration. So you can see from this picture up here, the tangential acceleration is pointed straight up. Radial acceleration is pointed towards the center of that circle. So in order to find the overall acceleration, which is going to be this thing that's at an angle, we have to use Pythagorean theorem. So we get acceleration is equal to the square root of the tangential acceleration squared plus the radial acceleration squared. And so plugging in numbers here, we get square root of 27.9 squared plus 28.66 squared. So we get the magnitude of acceleration, 27.9 squared plus 28.66 squared, square root of the answer. We end up getting 39.99, so about 40 meters per second squared for our overall acceleration. And then, of course, we're going to find the angle as well. So if you look at this, we're finding this angle theta. So this right here is our a sub t. So we can see that if we take the inverse tangent, that angle will be inverse tangent of the tangential acceleration over the radial acceleration. So angle here is inverse tangent of tangential acceleration, which was 27.9, over radial acceleration, 28.66. And we end up getting that our angle is equal to 0.772, and this is in radians because my calculator is in radians right now because of all the math that I've been doing with these rotational kinematics problems. So if we want to convert this to degrees, we then want to multiply this by 2 pi radians, 360 degrees. So times 360 divided by 2 times pi, we end up getting, we end up getting 44.2 degrees.